In the previous video we discussed diffraction. Now we will go through wave interference. This is chapter 5.2.4. By the end of this section you should be able to understand what is meant by the terms coherence, path difference and interference. Interpret the relationship between phase difference and path difference. Phase difference is measured in terms of angles, whereas path difference is measured in terms of wavelength. And what about coherence, path difference, interference? If you go to the end of this subchapter, you can see some definitions here. You should know them. Interference is the superposition outcome of a combination of waves. An interference pattern will only be observed under certain conditions, such as the waves being coherent. Coherent waves must have the same frequency, a constant phase relationship. This is very important. You have to know it very well. In the exams also they might ask you. I have seen this question in the past papers. They are asking you what is coherent wave. What is meant by coherent wave? So you have to mention this. The waves have the same frequency and a constant phase relationship. Now again, what about interference? That is also important. Is the superposition outcome of a combination of waves. By the way, what is superposition? I think we learned that in the previous lesson. Yeah, we have already learned that in the previous lesson when we went through superposition. So you should know what is superposition. Outcome of a combination of waves. And interference pattern will only be observed under certain conditions, such as waves being coherent. I am repeating this again and again because it's important. Now let's go to the beginning of the lesson. So coherence, path difference, interference, phase difference. Explain examples of wave interference. Two source interference. So we have two sources. In section 5.2.2 we saw that a wave meeting its own reflection would set up standing wave pattern, also known as an interference pattern. Reflection is a convenient way to generate coherent waves that produce a standing wave. Okay, so if you want to see the demonstration of this, you can refer the previous lesson where I had a demonstration. The incident wave gets reflected and then the incident waves and the reflected waves superpose to produce the standing wave. So it's in the previous lesson, and how a standing wave is formed. All of these are very important. Reflection, okay, so a wave pattern also known as interference. Reflection is a convenient way to generate coherent waves that will produce a standing wave. However, any combination of waves that have the same frequency and a constant phase relationship will produce this result. For example, now let's look at this. The loudspeakers are connected to the same signal generator, so they simultaneously produce identical sound waves. Both of these are connected to the same signal generator. So when this, as soon as this cone of the loudspeaker moves forward, this also moves along with it. So as soon as this moves back, this also moves back at the same time. So they are simultaneously producing identical wave sounds. Wherever the sound waves meet, they will superpose to produce a resultant displacement of air molecules. This means there will be points of maximum amplitude, antinodes, such as at position X. Now you see here, normally the wave front represents the crest of a wave, we can say, and the right in the middle of two wave fronts, which let's say are representing the crest of a wave, you have the trough. Okay, so crest and trough. If the crest and the trough of a wave meet, then you will have destructive interference. Therefore the displacement there will be zero as long as both waves have the same amplitude. So let's look at these positions X and Y. There will be points of maximum amplitudes, antinodes, such as at position X. So here you can see this wavefront and this wavefront meet there. Or points of zero amplitude. See, for example, here position Y. Why? Because this is representing the antinode, which is a crest, let's say, and between the two crests, for this you have the trough. So when the crest and the trough meet, we have destructive interference. Now we learned this in the previous lesson when we learned superposition. Now in this case, this is sound waves. So where you have a crest and a crest, or a trough and a trough meeting, you will have maximum amplitude. So you will hear a loud sound there. Where a crest and a trough meet, you will have destructive interference. Therefore, you will have silence there, or the minimum sound. That's what is explained here. This means there will be points of maximum amplitude antinodes. In the standing wave, you have the antinode and you have the node, such as at position X, or points of zero amplitude. Now why zero amplitude? Like I said, I'm saying the same thing again and again. When the crest and trough meet in the formation of a standing wave, when the crest and the trough meet, you will have a node there, zero amplitude, where there will be silence, such as at position Y. The relative positions of nodes and antinodes will depend on the distance from the speakers, their separation, and the wavelength of the waves. Yeah, so you can see it depends on the position of nodes, and will depend on the distance from the speakers, their separation, okay, separation of the speakers, and the wavelength of the waves. That's obvious. Two loudspeakers generating the same frequency sound. Two slit interference of torchlight. So we have torchlight, and then we have two slits here. So here we will have diffraction, here also you will have diffraction. Now this is a single slit, so the waves get diffracted. Then here there is no interference, whereas over here there is interference, because you will have diffraction from this slit as well as this slit. So on this side you will have interference. Another interference pattern. Now this, firstly we saw the interference pattern with sound, where you have minimum sound, silence, and maximum sound. Maximum sound is represented by an antinode. Minimum sound is represented by a node. So since the waves here are produced by the same signal generator connected to the loudspeakers, we can have a stationary wave created here. Stationary wave, sound wave. Similarly, we can have same thing with light, something similar with light. Another interference pattern can be observed if light is shown into an experimental setup that causes it to create two coherent wave sources that produce a standing wave pattern. Standing wave is also called stationary wave. This effect was first demonstrated by Thomas Young in 1803 using sunlight as the light source. A simple laboratory setup using a torch similar to that shown in figure B would show a pattern of dark and light fringes. You can see that here, dark and light fringes. See, this is the dark fringe, this is another dark fringe, this is another dark fringe, and in between the dark fringes you have the bright fringes. Would show a pattern of dark and light fringes that resembles the nodes and antinodes in a standing light wave. Here we have a standing light wave. Here we have a standing sound wave. Young explained his experiment using a theory that light behaves as a wave. In classical physics, interference is a phenomenon that can only occur with waves. Young's theory was highly controversial at that time, as he was contradicting Newton's theory that light behaved as a stream of particles. Despite the experimental evidence he demonstrated, most scientists at that time refused to believe Young's wave theory of light, because waves can have interference, like you see here. So this showed the wave behavior of light. See, in classical physics, interference is a phenomena that can only occur with waves. Two slits interference of torchlight and interference pattern of dark and light fringes is seen on the screen. investigating two source interference. So you can see the water waves here in a ripple tank. Two source interference demonstration in a ripple tank. I think previously also we have seen the ripple tank even in the IGCSE or O-level classes. You would have come across the ripple tank. A ripple tank where plane waves are diffracted through two small gaps will cause an interference pattern between the two water waves. So here we have a plane wave and then we have two slits here that will produce the interference pattern on this side, because here we have diffraction, here also we have diffraction. Therefore, this will result in interference. Alright, so this is from another textbook which is based on the Cambridge syllabus. You all are doing the Edexcel IAL syllabus, but I prefer using this textbook as well because it has more detail. So if you look at this diagram here, this is a ripple tank and this is a vibrating bar. Now this is connected to a signal generator where we can adjust the frequency at which this bar vibrates. We set it to vibrate and then it produces these plane waves. What do we mean by plane waves? Plane waves, if I zoom in here, you can see have parallel wave fronts. See, these are horizontal lines here. You see there are, I think you can see two lines there. Let me zoom in some more. Yes, yeah, there are about three lines here. 1, 2, about, yeah, 3 to 4 lines here. Clearly you can see two lines here. So this will vibrate up and down, we can say. So that will produce water waves which are plane waves, meaning they have parallel wave fronts. At a constant rate this will produce that. So they have a constant wavelength, constant speed, frequency, we can say. Now here we have a barrier and there is a gap or aperture here. So this gap is approximately equal to the wavelength of these waves. Therefore you will have prominent diffraction. The waves are diffracted at this gap. In the book that we saw, we had two of these gaps. So therefore it produced, so here is one gap, we can say here is another gap. So it will produce the diffraction pattern from here and also from here. And what will happen? Those circular wave fronts. Here we have plane wave fronts, here we have circular wave fronts. Those circular wave fronts from here and also from here will interfere to produce a pattern. And in a previous video, in a previous lesson, I think we saw under superposition, we saw this actually created in water waves and what it looks like. So you will have areas where the water, and by the way you will have a standing wave created here. The standing wave will have nodes and antinodes. So therefore you will have areas where the water is flat, it's neither up or down, and other areas where there are like bumps in the water because there is constructive interference there. So you have constructive interference where you have maximum amplitude, or it corresponds to, let's say, in a wave, in a standing wave, the antinode, and then you have areas where the displacement is 0. Okay, now we can also do this using two dippers. Instead of using two gaps, it can also be done in the ripple tank using two dippers. Let me show you what I mean. Okay, this is the one. See, here you have the two dippers. A ripple tank can be used to show how two sets of circular ripples combine. So we have circular wave fronts here, and this is one dipper. Now you can see it's connected to the same vibrating bar. So this vibrates at a rate that we want, and it's a constant rate. So therefore it will produce these ripples, circular ripples or circular wave fronts here. So here you have circular ripples, here you have circular wave fronts, and then they interfere to produce the standing wave. Now let's go back. A ripple tank where plane waves are diffracted through two gaps will cause an interference pattern between the two water waves. Another common experimental demonstration of two slit interference is with laser light. Okay, laser light, you can see this is the double slit, and by the way it's not this big, but they have drawn it large so that you can see it in the diagram. But remember that beam, laser beam, should be having a diameter much bigger than the two slits combined with their gap. Okay, so this is drawn like this so that you can see it. Okay, but this is very small, and remember, for diffraction to occur, the size of the slit should be equal or approximately equal to the wavelength of the waves. So here we have laser light. Laser light is in the visible range. Remember, the visible range is from 400 to 700 nanometer wavelengths. So red is in the longer wavelength area. Now therefore the size of these slits should be so small so that it can cause diffraction, and here you will have diffraction, here you will have diffraction, that will result in interference here to produce these bright spots. And I think we call this Young's double slit experiment, two slit interference demonstration with a laser. The two source interference and two slit interference are the same thing. In both cases, two waves are brought together to produce an interference pattern. Two slit interference is a form of two source interference, where slits diffract existing waves in order to act as new sources of waves. So here it's like a new source of waves, here also it's like a new source of waves. Okay, so you can see the slits here and here. These are the two slits. Different distances from each slit to point x determine the resultant amplitude of the standing wave at x. Now remember, here we have a standing wave. So where you have the crest and the crest, or the trough and the trough meeting, you will have constructive interference there. So the crest of this, and then of this it should be also the crest to have constructive interference. If it's crest and trough meeting, crest from one wave meeting the trough from the other wave, will result in destructive interference. So that will correspond to a dark spot. Where you have constructive interference is where you have the bright spots. Different distances from each. Okay, so each point into source interference pattern will have a superposition result that depends on the phase difference between the waves coming from each source to the point. That phase difference will in turn depend on the relative distances to the point from each of the slits compared with the wavelength. In figure E, imagine the distance from the slit to x along the blue line is 100 wavelengths, and the distance along the red line is 115 wavelengths. So from here to here, imagine we have 100 wavelengths. From here to here, 115. Now remember, we talked about path difference earlier. Path difference can be found here. That is the difference between the number of wavelengths between these two. So it will be 115 minus 100, which is 15 wavelengths. The path difference of these two waves at point x is 15 wavelengths, as the path difference is exactly 15 wavelengths. The waves will be in phase at point x and will constructively interfere to produce a maximum resultant, as in an antinode. So we have exactly a whole number, or a natural number of wavelengths. Therefore there will be constructive interference there, which means you will have an antinode. But if you have the difference to be a natural number plus half. So like 15 and a half, 12 and a half. So the difference will give you a whole number and a half, or just a half. In that case, the crest and the trough meet. So we will have destructive interference. So now you understand, when there is destructive interference, we have path difference of natural number plus half, or just half even is fine. And when we have constructive interference, the path difference will be only a natural number of wavelengths. So if it's a natural number plus half or just half, that is the path difference, then we will have destructive interference. At that point we will have a node where the crest and the trough meet. Okay, if it's a whole number of wavelengths, if the path difference is a whole number, or we can say natural number of wavelengths, whole number or natural number, it's better to say whole number of wavelengths, then we will have constructive interference, which means the crest and the crest, or the trough and the trough, are meeting, and it produces an antinode at that point. Antinode has the maximum amplitude, node has zero amplitude. So at x, since you have a natural number for the path difference, the waves will be in phase at point x. So that means the crest and the crest, or the trough and the trough meet, and will constructively interfere to produce a maximum resultant, as in an antinode. If we passed laser light through the two slits, then point x would show a bright spot on a screen placed there. Now remember, I told you the bright spots correspond to constructive interference. Between the bright spots you have dark spots, they correspond to destructive interference. Previously, when we learned superposition, we have learned these things in detail about constructive interference, destructive interference. Alright, let's look at this. I think we saw a video of this kind of demonstration in a river, I think, or lake previously, and you could see in that video these lines were shown. So what are these lines? The red lines join the intersection of the wavefronts. So where the two wavefronts intersect is where we have the crest and the crest, or the trough and the trough meeting. They correspond to constructive interference. So they are, if you go along any of these red lines, you will have a node there, antinode there, because you have constructive interference. The crest and the crest, or the trough and the trough, are meeting. Whereas if you go along the dashed green line, you can see the dashed green line is joining the points where the crest and the trough meet. That means it's joining. Now we have the waves coming out from here diffracting, and also the waves coming out from here that are diffracted. So waves are diffracted here. Now see, this is the plane wave, a wave front of the plane wave. So that comes here. It will undergo diffraction at this slit, and again the same plane wave front will undergo diffraction at this second slit. And on this side you will have the waves from this slit and this slit interfering to produce the standing wave. Okay, so what about the dashed green line? Like I said, the dashed green line is joining the places where the wave front and the middle of two wave fronts meet. So you see, for example, here this is the wave front here, and also it's in the middle of two wave fronts from the other wave. So that means wave front means we can say crest. Between two wave fronts, that's the trough. So the green lines join where the trough and the crest meet. Trough means you have maximum amplitude, crest means you have minimum amplitude. So they are in phase, they are coming from the same source, so they will have the same amplitudes. Okay, so same amplitude, one is positive, one is negative, therefore you will have zero displacement. Yes, so here is the explanation. I already explained it. All points that are exactly in phase where the path difference is a whole number of wavelengths, n lambda, whole number of wavelengths. So when you take the number of wavelengths, say from here to a certain point, let's say here, and the number of wavelengths from here to here. See, we can even count it right now. Let's see. So here you have, let's consider this point, all right? So you have 1, 2, 3 and 4 wave fronts. Let's look at this starting here. 1, 2, 3, 4, 5, 6. See, from here it's 6 wave fronts, from here it's 4 wave fronts. So at this point we can say the path difference is 2 lambda. Okay, 2 lambda. So it's a whole number of wavelengths. Therefore we will have constructive interference here. Actually, when it's a wavelength, okay, now we don't really count the wave fronts, because from one wave front to the next wave front, that is a wavelength. Okay, but the problem is here. So we are not sure whether from here to here it would be one wavelength. So that is the little bit of a problem. Now if this was a straight line or just the curve there, then yeah, we can count. But if we count it, okay, so 1, 2, 3, 4, that's what I counted. Okay, so from here to here, one wave length. So this is the first wave front. From here to here, I assume it's one wavelength. So first wave front is from here to here, one wavelength, then second, 2 wavelengths, third, fourth, like that, 4 wavelengths to this point. Then again from here, 1 wavelength, 2, 3, 4, 5, 6 wavelengths. So 6 minus 6 wavelengths from here to here minus 4 wavelengths from here to here, we will get 2 wavelengths. Therefore, the path difference is 2 wavelengths. Now let's look at another point. For example, here, or even here, because it's easier to count. Okay, so here, now look at this. We have 1, 2, 3, 4, 5, 6 wave fronts from here. 1, 2, 3, 4, 5, 6. Yeah, here up to here. Okay, 6 wave fronts. This point. See where it is labeled destructive interference. Okay, from here it's 6 wave fronts. Now from here how many? 1, 2, 3 and a half. So 6 minus 3 and a half. That is 3 and a half. So 6 minus 3 and a half. It's 2 and a half, right? So again you have a whole number part and a half. So that means, remember I told you earlier, if it's a whole number or natural number plus a half, okay, instead of saying natural number we can say whole number. What is whole number? Whole number are all the counting numbers and 0. So 0, 1, 2, 3, 4. So those are the whole numbers. Okay, so it's better to say whole numbers, because when we say natural numbers, yeah, we have the counting numbers. Okay, and then we have integers, which are also natural numbers, and they are negatives. Okay, counting numbers, natural numbers, counting numbers. That is what is explained here. All points that are exactly in phase where the path difference is a whole number of wavelengths, n lambda, will produce constructive interference. Constructive interference. Any points where the path difference is given by this. So if you substitute 1 here, you will get 3 over 2, which is 1 and a half. So you have 1 and a half. See, that is corresponding to destructive interference, will cause destructive interference. The connection between the phase difference and the path difference comes if we remember that each complete cycle or wavelength corresponds to 2 pi radians in phase. Waves from one slit meeting waves from the other slit at a point will each travel, will each have had to travel to that point. Now see, phase difference in terms of wavelength, path difference is in terms of angle. I think in the previous lessons we saw that one whole wavelength can correspond to 360 degrees or 2 pi radians, because 2 pi radians is 360 degrees. And I also think we saw the unit conversion from degrees to radians and radians to degrees. Okay, so the connection between phase difference and by the way, so 2 pi radians is equal to 360 degrees. That means pi radians is equal to 180 degrees. You can remember that conversion factor. Pi equals 180 degrees. Pi radians is equal to 180 degrees. And then you can use that to convert between radians and degrees. The connection between the phase difference and path difference comes if we remember that each complete cycle or wavelength corresponds to 2 pi radians in phase. Waves from one slit meeting waves from the other slit at a point will each have had to travel to that point, cycling through wavelengths as they go. Thus, by comparing the path difference, this can be converted into phase differences. So, when you know the path difference, using that conversion factor I told you, pi radians is 180 degrees, you can find the phase difference from the path difference, or from the path difference you can find the from the phase difference path difference, or from path difference phase difference, using that pi radians is equal to 180 degrees conversion factor. Points where the path difference is equal to n lambda exactly will have a phase difference of 2 n pi, because remember a phase difference of one wavelength is equal to 2 pi radians or 360 degrees. 2 n pi exactly, and will be in phase, producing constructive interference. Points where the path difference is equal to this exactly will have a phase difference of 2n plus 1 pi. 2n plus 1 pi. Now, how did they get that? Remember, pi over 2 is, now see if you look at this, 2n plus 1 is there, 2n plus 1 is here. Pi over 2, that is half a wavelength. Now, full wavelength is 2 pi, half a wavelength is therefore pi or 180 degrees. So, that's where we get that. So, it will be pi over 2, remember, one whole wavelength is equal to 360 degrees or 2 pi radians. Therefore, pi over 2, half a wavelength is 180 degrees or pi radians. Exactly, and will be in antiphase, producing destructive interference. Okay, so now you know about path difference and phase difference. You have learned about constructive interference, destructive interference, and how waves interfere. You learned about coherent waves. We went through these definitions. So for this interference to happen and to produce the standing wave, the waves must have the same frequency and a constant phase relationship, which means the waves must be coherent. So if they are coming from the same source, they can be coherent. Alright, that's the end of that lesson on wave interference. And we have actually completed that chapter on that topic. So remember, this is what we already went through in the first 5.2.1, chapter 5.2, behavior of waves. Remember the angle, how I told you how to convert between the units. Then we also talked about the stationary wave. In a string, the stationary wave, see, and there is a video. Those students who purchase the complete course will have access to everything here. And the details of the complete course or the link to purchase it should be in the video descriptions. You can also contact me, and then I can share it with you. And you can also join our live online sessions. If you buy the complete course, then there will be complimentary live classes that I can include. And by the way, this lesson I am recording here was also a class that I conducted to a student online. I have never met the student in person. It was conducted online. So you all also can join from any part of the world. Easiest, the fastest would be to contact me. The contact information is in the video description. So again, all these definitions are important. Then last video we discussed diffraction. Remember the diffraction grating equation is very important. And then I explained the diffraction grating using this diagram as well. And in this video we discussed wave interference, and that's the last one. And make sure, like I have always been saying, you answer these questions and check the answers to this book. Make sure that way you know you're doing the things correctly. And you can answer the end of chapter or exam style questions as well. Do them and check the answers. The answers are also available. So better to do all of them. They are not that difficult, I guess. So these are the past paper type questions that you can get. Okay, so that's the end of that lesson. Make sure you go through the video description. There is some useful information there. And the entire course is available online for purchase. You can do it at your own pace from any part of the world. If you're having an internet connection, that means you are having everything that you need to follow this course. There are theory explanations, videos containing them, notes, solved past exam papers, and tutorials. Everything you need to get an A is included in the course. The IAS and IAL are also available separately for purchase, or you can buy the entire course at once. And if you don't want to buy our courses, if you want to join only the online classes, that option is also available. You can contact me for more information about it. You can do it from any part of the world as long as you have an internet connection, which means if you are watching this, you have all the requirements to join the online class. Alright, so I hope to see you all soon in the next video.